All right, good morning. Just going back to functions and inverses. And again, for one-to-one functions and their inverses, okay, they're going to compose together as x. And again, the graphs of one-to-one functions and their inverses will have symmetry with respect to the line y is equal to x. And for what we have from page 365, now we have a couple of functions where we have h of x is equal to 7x minus 3, and we have k of x is equal to x plus 3 over 7. And we're looking to see if these functions have an inverse relationship, okay, as in where we have the determination of whether they will compose together as x. Okay, so for the first part, okay, so if I have h composed with k of x, okay, and so just clustering the functions together, okay, just translating where we have h of k of x, okay, and so we're going to have h of x to be dependent upon the behavior of the function k of x. And for what we have in terms of operating in line with the outside function, okay, so you have h is on the outside, okay, and so we have for h of the input, again, the mode of behavior is where we're going to have 7 times the input minus 3. And we have with the input at k of x, okay, so h of k of x is going to be 7 times k of x minus 3. And for k of x, again, that is defined as x plus 3 over 7. Okay, so you have 7 times x plus 3 over 7, followed by the subtraction of 3. Okay, and so for what we have in terms of carrying out what we have here, okay, so we're going to have 7s to cancel. And so for what we have in the follow through, okay, so we have x plus 3 minus 3. And 3 and negative 3 will cancel out, so this will lead us to x. Okay, so far so good. And if we do it the other way around, okay, and so we have k composed with h of x. Okay, so we now have k of h of x. And we have for this particular case, all right, so we have operating in line with k of x. Okay, so we have k of x is equal to x plus 3 all over 7. All right, so we're looking at, in this particular case, for the input as h of x. Okay, so we have h of x plus 3 all over 7. And putting in the expression that defines h of x, so we have 7x minus 3, followed by the addition of 3 all over 7. And again, we're going to have the 3 and the negative 3 to cancel. So this will come down to 7x over 7. And so that is equal to x. Okay, and so we have both compositions, okay, to come out to x. And since we have unanimously the composing of the functions to end up at x, the answer to the question is yes. Okay, they are inverses of each other. And for what we have in the case of number 34, okay, so you have another pair of functions, And we're looking to see if we have an inverse relation. And for what we have in the case of the first function, okay, so we have p of x is equal to negative 3 plus x all over 4. And we have q of x equals 4x minus 3 and looking at composing together, you could either do q composed with p of x or p composed with q of x. And we'll just have p composed with q of x. Okay, so this will lead to p of q of x and again operating in line with p of x. Okay, and again, so we have with p of x we have equal to negative 3 plus x all over 4. Okay, and so we're looking at negative 3 plus q of x all over 4. And so for what we have here, okay, we got negative 3. And filling in for q of x, okay, so you have the binomial 4x minus 3 and as we combine terms, okay, notice, okay, we have 4x and if I had the cancellation of the constants like what I had presented in number 32, okay, I would have the composition to reduce to x. But for what I have instead, I have negative 3 to repeat, and so those would combine to negative 6. So I have 4x minus 6 all over 4. And guess what? In terms of the reduction, that is not going to come out equal to x. And you don't even have to take the other composition. Okay, so if we don't have the composition between the functions to reduce to x from the get-go, you don't even have to do the other composition. Okay, so we have, in effect, since the composition does not come to x, okay, it turns out that p of x and q of x are not inverses. All right, now, in the case of looking at a provided one-to-one function, okay, and trying to configure what the inverse is going to be, and we have, for number 41, okay, we have a given function, f of x, is equal to 4 minus x over 9, and I'm going to pause for just a moment. Okay, now for 4 minus x over 9, I just want to stress something. Okay, if I were to change the order and separate this fraction into distinct terms, so we have negative 1/9 of x plus 4/9. Okay, and I just want to say something about this. Okay, if you notice we have negative 1/9 of x, okay, as the term that defines the nature of the function, okay, and this is going to be a linear one-to-one function, And again, for what we have in the case of linear one-to-one functions, and so we kind of let's see. There we go. All right. So you just had to do a little bit of a reboot. Okay, so you have linear one-to-one functions and their inverses. Okay, so linear one-to-one functions and their inverses, and I will place emphasis upon the linear. We'll have the set of all real numbers for their domains and ranges. Okay, and just taking what we have now. Okay, so we're starting out with f of x is equal to 4 minus x over 9. And then looking at what we have in the case of the inverse. Okay, so we have f of x. Again, that is its own way of saying y. So you have that y is equal to 4 minus x over 9. And crossing over into the determination of the inverse. So again, I'm going to interchange x and y. Just a moment. My computer's just acting up today, I guess. Okay, so for what we have in the case of interchanging x and y, okay, so we're going to have the x is equal to 4 minus y all over 9. And we have multiplying by 9. Okay, so we're going to have 9x is equal to 4 minus y. And looking at isolating, okay, the y term. Okay, so if I take 4 away from both sides, so we have 9x minus 4, okay, is equal to negative y. And if I multiply or divide the equation by 1, okay, so just changing the signs here. Okay, so in this case, we're going to have negative 9x plus 4. Is equal to y, and then we have upon switching sides, okay, so we have that y is equal to negative 9x plus 4, and then just formally declaring the inverse. Okay, so we start out with f of x And so we're going to have the inverse of f of x is going to be equal to negative 9x plus 4. Okay. And again, the domains and ranges will be all real numbers throughout. Okay. And just kind of taking a view of what we have here. And we have upon zooming in, okay, so we have for f of x is equal to 4 minus x over 9. Again, the inverse, okay, we have negative 9x plus 4. And their graphs will have symmetry with respect to the diagonal line, which we have at y is equal to x. And again, we're going to have interchanging x and y terms. Okay, so you have negative 5, 1, 1, negative 5, 0, 4, 4, 0, and negative 1, 13, and 13, negative 1 among the sampled ordered pairs. All right. Now, in the case of one-to-one functions and their inverses, now we have, in the case of item 43, now we have a nonlinear one-to-one function, okay, with h of x. And for what we have in this particular case, right, so we have with h of x equal to the cubic root of x minus 5. I'll just mention, just kind of lay out what we have here. Now, because of the nature of the radical being a cubic root, you don't have the restriction that x minus 5 cannot be negative, as would be the case if you had an even root radical. So I'm just going to state that for the domain of h of x, okay, we're going to have the set of all real numbers and if x can be anything, well, guess what? Y or h of x can be anything as well from the real number system. Now, just go ahead and mention, okay, now for the case of what we have for the inverse, which we will get to. For the domain of the inverse, again, I'm going to use a little bit of color coding. So what we have in y for the original function, we're going to have an x for the inverse. So you have all real numbers for the domain of the inverse. And for what we have in the case of the range of the inverse, again, what we have in x for the function, we're going to have in y for the inverse. Okay. All right. Now, in looking at what we have for the inverse of the given function, Again, so you have h of x is equal to the cubic root of x minus 5. Okay, and again, just translating in terms of the variables x and y. So you have y is equal to the cubic root of x minus 5. Okay, and then once again, just crossing over into the threshold of determining the inverse. And we have upon interchanging x and y. Okay, so we have x is equal to the cubic root of y minus 5, and then to free up the y expression. Okay, so if I take both sides and raise to the third power, okay, so we're going to have x cubed is equal to y minus 5. Okay, and we have in following through. Okay, so if I add 5 to both ends, okay, so you have x cubed plus 5 is equal to y, and if I just switch the order upon taking the commutative property of equality, in other words, going from b is equal to a is equal to b form, okay, so you have y is equal to x cubed plus 5. And so we're going to have for the inverse. Now I started out with a function defined by h of x, and so just preserving that letter, and we have, and using inverse notation. Okay, so we have the inverse of h of x is going to be equal to x cubed plus 5. Okay. And just looking at the dynamics, okay, that will be played out. And once again, the domains and the ranges, okay, will be all real numbers. And we have with the curves, okay, so you have in red, okay, you have the graph of y is equal to the cubic root of x minus 5. And for what I have for the inverse, you have x cubed plus 5, so you have this curve in black. And again, both of these graphs will have interchanging x and y values and will run and have symmetry with respect, okay, to the line, okay, y is equal to x. All right. Now, where we do not have the domains and ranges, okay, to consist of all real numbers, now we have in the case of the next item, and we have with our function, and we have a precondition that is laid out. And we have in the case of number 53, okay, so you have a function f of x is equal to x squared minus 3. And we have the condition laid out, okay, where we're going to have the x is less than or equal to 0. Okay. Now, one question posed is whether this function is going to be 1-to-1. Okay. So just looking at what we have for the graph of this function, so you have f of x is equal to x squared minus 3. And just doing a bit of a rough sketch here. So you're going to have a parabola, or part of a parabola, since I have x is less than or equal to 0. So you're looking at where x is going to be in the negative zone. So this is going to be our graph of f of x. So you're looking at the left half of this parabola, since we have x is less than or equal to 0. Okay, and to be a function, it has to satisfy the vertical line test, and to be one-to-one, okay, it must also satisfy the horizontal line test, meaning that for each y value there can be no more than one corresponding x value. Okay, so this particular function is one-to-one. And just taking what we have with the description that we have for this function. Okay. All right. So we got here. I'm just going to mention, okay, so we have in the description, we have that x is less than or equal to 0. Okay, so just for what we have for starters. Okay, so we got for f of x equal to x squared minus 3. And this is already in the illustration. The smallest possible y value is going to occur whenever x is at 0. Okay, and so for the smallest possible y value, okay, this will come out to negative 3. Okay, and just taking what we have here, okay, so we have the smallest possible y value, okay, so the minimum y is equal to negative 3, okay, and okay, so for what we're going to have, notice we have x is less than or equal to 0, and the minimum y we have equal to negative 3. Okay, so for the domain of f of x, okay, so we have in the case of the domain of f of x, okay, so again we have the x is less than or equal to 0, and so we have, just take, okay, so we have the domain of f of x, again, so we have going from negative infinity, approaching and including 0. So it's from this particular part. And as for the range of f of x, Okay, and again, the minimum y value, okay, was at -3. So we have for the range, we're going to go from and including -3 on out to infinity. Okay, and for what we have in the case of the inverse. Now, I haven't gotten to the inverse yet, but we have the details in terms of its domain and range. So we have for the domain of the inverse. Okay, so that's going to go from x equal to -3 and heading on out to infinity. And for the range of the inverse, again, what we're going to have in y is what we had in x for the original function. Okay, so we have from -infinity up to and including 0. Okay, all right, so we have in the case of looking at the inverse. Okay, so we have starting out with f of x, okay, equal to x squared minus 3. And then just tacking on, okay, the conditions case, you have x is less than or equal to 0. And again, we have for y, again, you will have that y is greater than or equal to -3. And rewriting f of x in terms of y, which we have equal to x squared minus 3. And then looking for the inverse. And again, if I interchange x and y, okay, so we're going to have the x is equal to y squared minus 3. And this time around with interchanging x and y. Okay, now what was required for x and y for the original function, we're going to have switched around. Okay, so we're going to have this time that x is greater than or equal to -3. And that y is going to be less than or equal to 0. Okay, and so here we're looking at solving for y. And right now our y term is on the right with y squared. And upon isolating y squared, and I'm just going to repeat these restrictions. Okay, so I have x plus 3 is equal to y squared. And we'll have in terms of the follow through, again, we have with the square root property of equality. And I'm just going to switch the sides here. Again, we have with the square root property of equality. Okay, so I'm going from y squared to y. And that's going to be equal to plus or minus, okay, the square root of x plus 3 so again, we have x is greater than or equal to -3, and we have y is less than or equal to 0. Now, for y is equal to plus or minus, okay, the square root of x plus 3. Okay, again, notice that if y is not equal to 0, it is going to be negative, and that less than 0 part signals that we're going to go with the less than part. And so it's going to follow that for the inverse, we have the inverse of f of x. Okay, this is going to be the negative of the square root of x plus 3. Again, you would have with the restriction this time that x is greater than or equal to negative 3. And again, just to restate, you had that y is less than or equal to 0. And just give you a bit of a visual. And we have taking what we have, say, in Desmos. Okay, now if I had f of x equal to x squared minus 3, I would have the whole parabola. But I'm looking at those values less than or equal to 0 for x. So if I just take the portion whereupon we have the x is less than or equal to 0, so I have this left half of the parabola. And again, we're going to have a one-to-one function, since this will satisfy both the vertical and horizontal line tests. And again, we have, again, we're going to have a one-to-one function, and its inverse will have symmetry with respect to the line y is equal to x. And for the inverse, again, so we have g of x, which will represent the inverse. Okay, so that's going to be the negative of the square root of x plus 3. And okay, so I didn't have to throw in the added condition here, but I'm just going to kind of repeat here. So you have on the condition that x is greater than or equal to negative 3. A little bit of a redundancy, but just wanted to stress the restrictions and just taking some of the numbers here. So I have negative 3, negative 2, negative 1, and 0. And just putting in ordered pairs. Okay, so I had negative 3, 6, but if I go the other way, I have 6, negative 3, 1, negative 2, negative 2, negative 1, and negative 3, 0. And again, so you have this function to be one-to-one, and it does reflect about the line y is equal to x with respect to, okay, it does it have ordered pairs where the coordinates will be interchanging. Okay, so f of x and g of x, they are inverses of each other. All right, and we have in the case of the next item, and we have again, the functions we have dealt with so far have been your typical algebraic expressions like involving fractions, polynomials, where we had the interchanging to involve the four operations with addition, subtraction, multiplication, as well as division. Now, there is another case here of another kind of one-to-one function, and this will be with the exponential functions. And we have, in the case of exponential functions and their inverses, Okay. Now we looked at, say, like undoing radicals by using exponents, and have undone multiplication by division and vice versa, and in some cases addition by subtraction and the other way around. Now, for a given function f of x, is equal to a to the x, and just some of the items we have here. Okay, we have an exponential base a, and for this one, okay, this will be defined by the characteristics where a is going to be positive with the exception of 1. And for f of x, okay, that is going to be a positive value. Okay, and for what we have in the introductory case, all right, so you have, if I'm looking for the inverse of this function, okay, so you have f of x equal to a to the x, again, putting in terms of y, so you have that y is equal to a to the x. And looking at interchanging x and y, once again, in creating the path forward to finding out what the inverse is going to be. So we have the x is equal to a to the y. Okay, now I'm still trying to get the y by itself. Okay, and the only way we can get y by itself is that I'm going to have to somehow eliminate the presence of a. And this will not be with your typical operations of addition, subtraction, multiplication, or division, or even taking radicals for that matter. There is a separate operative, and this will be taking logarithms. And we'll be taking logarithms in the base that's going to match the exponential base, which in this case is going to be at a. And before I proceed, let me mention, okay, we start out with a is greater than 0 with the exception of 1, and we had that y is going to be greater than 0. Now we still are going to have the same restriction for the exponential base a, because in spite of the interchanging, a still plays the same role. But after interchanging, it is now not y but x in this formation that has to be greater than 0. All right. Now, in converting a to the y in terms of y, we're going to take what we refer to as a base a logarithm. Okay, so we have the base a logarithm of x is going to be equal to, and if you have a logarithmic term where you have connecting together a base a logarithm with an exponential base that has same variable or number that matches the subscripted term, then those items are going to cancel out, and what is the power is going to be the reduced result. So we're going to have that y is equal to the base a logarithm of x. And so for what the inverse is going to be, okay, so we're going to have the inverse of f of x is equal to the base a logarithm of x. And again, we still have, well, a is now going from exponential to logarithmic base. It is still going to be a positive value with the exception of 1. And again, we have this time the x has to be positive. Okay, and so we have in terms of definition. Okay, now commonly posed question is, what is a logarithm? And we have by definition, okay, now a logarithm is going to be the inverse of an exponential function. Okay, and just give you a bit of a sample here. There might be some of you who are taking physics or dealing with acid-base calculations in chemistry. We have involving, okay, the base 10. I'll give you just a case here. Let's say you have with the exponential base at 10. Okay, so if we have f of x is equal to 10 to the x, and I'm looking for the inverse. Okay, so we have like y is equal to 10 to the x. And again, if I interchange x and y, okay, so I have the x is equal to 10 to the y. Okay, and so I'm at this point, like along the stage of x is equal to a to the y. And again, to take care of y, okay, you have a to be at 10. So I'll be looking at taking what will be referred to as a base 10 logarithm. Okay, so we have a base 10 logarithm of x is equal to y. And just switching the order, we have that y is equal to the base 10 logarithm of x. So we have for the inverse of 10 to the x. We want to have this to be equal to the base 10 logarithm of x. Okay, and just taking a bit of a sampling. Okay, so if I have x at 1, 2, 3, and 4. Okay, and for the corresponding y value, okay, so I have like in powers of 10. Okay, like 10 to the first is equal to 10. And for x at 2, now y is going to be 10 squared, which is going to be at 100. And for x at 3, okay, so you have 10 to the third, which will be 1,000. And for x at 4, okay, so you have 10 to the fourth, it's going to be at 10,000. So you would have, say if you were to have graphed, okay, you would have among the points, you would have 1, 10. You would have 2, 100. As well as 3, 1,000. Then we have 4, 10,000. Now let's say that if I have y is equal to the base 10 logarithm of x. Now this feature is going to be in your calculator. Okay, and if you got a scientific calculator, and it's going to have the appearance as log, so just a standalone log. Okay, that's in reference to a base 10 logarithm. let's say if I have x at 10, 100, 1,000, as well as 10,000. Okay, so just in calculating, so if you have like log of 10, you might press 10 then log, or you might have log then open parenthesis 10 close parenthesis and then hit enter, so that's going to be 1. And for base 10 logarithm of 100, that is going to go to 2. And for that of 1,000, okay, that will go to 3. And for the base 10 logarithm of 10,000, okay, that is going to go to 4. Okay, so if you notice we have with the ordered pairs, okay, this will go to 10, 1, 100, 2. $1,000 for x, 3 for y, and finally we have 10,000 where the corresponding y value is going to be at 4. So again, if you notice, we have interchanging x and y values. And again, in this instance, okay, we have a base 10 logarithm is going to be the inverse of an exponential logarithm, where we have to be the inverse of 10 to the x. Now there is another number that is also a common logarithm, okay, and this is it's going to have an infinite number of decimal places, and we're not talking about the number pi, but it could potentially be applied in geometric or trigonometric fashion. And just to kind of start things off, okay, and we have say we have in the categories, so we have x, we have 1 plus 1 over x, and we have 1 plus 1 over x raised to the x. And just some of the numbers here, okay, just for x, I can start off with 1, as well as 2, and also with number 5. You see, you have 10. You see, you have 100. And say we have going all the way out to 10,000. Okay, so we have for, if x is 1, we have like 1 plus 1 over 1 is going to be 1 plus 1, which will be 2. 1 plus 1 half will be 1.5. 1 plus 1 fifth, okay, that is going to be at 1.2. And then you have 1 plus 1 tenth, so you have 1.1. Then you have 1 plus 1 over 100. We'll have this as 1.01. And for 1 plus 1 over 10,000, you have 1.0001. And guess what? For 1 plus 1 over x to the x, you have like 2 to the first, 1.5 to the second, 1.2 to the fifth, 1.1 to the 10th, 1.01 to the 100th, and 1.0001 to the 10,000. Okay, so you have a bit of countercurrent things going on. Okay, the sum is getting smaller as the power continuously gets larger. Okay, so we have for 2 to the first, okay, this will go to 2. The square of 1.5, okay, this will go to 2.25. For 1.2 raised to the fifth, okay, this number we have like 2.48832. Now for 1.1 to the 10th, you have among the first digits, you have 2.5937. And for 1.01 to the 100th, okay, you have a number just over 2.7. And for 1.0001 to the 10,000, you have 2.71814. Okay, and if you notice, okay, now the transition from the exponent from 1 to 2 to 5 to 10 to 100 to 10,000. Notice that you don't have much of a change, and it's like once you get past the threshold of the 10th degree to the 100 to the 10,000, it's like the rate of change becomes increasingly negligible, and x could continue to grow continuously, and there is a saturation point that is going to be reached, and as x approaches infinity, what's going to happen here is that we have 1 plus 1 over x to the x is going to approach a particular value, okay, and this will be in the form of a letter. And it's not going to be the Greek letter pi, it's going to be this number here, which will be the letter E. And this value E, okay, if you were to enter this into your calculator, like just E or E to the first, you have among your first digits, you have like 2.718, 28, and like 18, and this is going to flow continuously, and there's not going to be a last decimal place, just like the number pi. And now for what we have in the case of E is what is regarded as the natural logarithmic exponential base. And just some of the notations in your calculator. Okay, just with a LOG. LOG refers to a base 10 logarithm. Okay. And so you have like LOG of x. This will be the same as the base 10 logarithm of x. Now, you might have either above it, below it, or just alongside the LOG. Again, we have ln. ln is going to refer to a natural or base E logarithm. And for what you're going to have in the case of ln of x, that's going to be the same as a base E logarithm of x. So in your calculator, if you're referring to a base E logarithm or natural logarithm, you got ln. For base 10 logarithms, you have log. Okay, and now the logarithms, like base 10 logarithms, can have applications in many of the scientific fields. And for the base E logarithms, okay, they can have an application in the realm of finance. And let me give you just a bit of a segue here. for what we have regarding interest and finance. And just kind of going from one stage to the next. It'll be a little while before we get to the exponential base e. But we have in the first stage, okay, we have what's going to be referred to as simple interest. And if you're taking business courses, you probably have seen this formula or some variation of it. Okay, now for simple interest, okay, we have that I is equal to P times R times T. And from this, we have the A is equal to P plus I. Now in terms of what the letters represent, okay, so you have I is going to be the interest amount. Okay, now for P, that's going to be the principal, which will be the amount financed. Okay, now R is going to be the rate of interest. And this is going to be displayed in calculations as a non-percent decimal. Okay, and for what we have in the case of T, okay, T is going to be the amount of time in years. And for A is going to be the future value. We have what is financed plus the interest that is built upon it. Okay, so when one refers to interest, it could be simple interest. But if you're looking at a long-term situation, okay, we might also be referring to compound interest. You have a lot of the same characters from the simple interest, okay, and this is going to be involving an exponential function. Okay, so you still have A, future value P, what is financed, times the quantity of 1 plus. You still have R for the rate of interest. Now the new variable is going to be the letter N, so you have R over N, and we have raised to the N times T. Okay, now everything else being the same with A, P, R, and T. Now N is going to be referred to as the compounding frequency. And what I mean by this, okay, if you look at it on a yearly basis, okay, you have some of the descriptive language. Okay, so if you have like annual compounding, okay, that means we have one time a year. Okay, so N is equal to 1. And if you have the term like semi-annual, that's like once every 6 months, or in this case, twice a year. And if we have in the case of quarterly compounding, So you have that n is equal to 4. And for monthly compounding, okay, so you have the n is equal to 12. And now for daily compounding, now there could be those institutions that like to stick with the base 10 arithmetic as much as possible, where it might just consider 360 business days in a year, but more and more, I think most will go with the typical 365 calendar days per year. And okay, so you have these various numbers for n. And let's say that, just kind of give you an example with compound interest. And say we're looking at determining a. And we'll say we have, in the case of the principal, okay, so let's say that we have P is equal to $5,000. And we'll say we have the time span will be for 6 years. And we'll say that for the frequency, you have 2 semi-annually. And I think that with stuff like the federal government treasury notes and stuff, I think their compounding is done semi-annually. And we'll say that we have for the rate of interest, okay, so you have R is equal to, we'll say 3%. And as a decimal, okay, this will come out to 0.03. Okay, so if someone is putting into an account, let's say $5,000, and let it just sit there, nothing taken out, nothing added. And after the 6 years, after compounding twice a year at a rate of 3%, we want to find out what that $5,000 will grow to. So again, we have A equal to P times, okay, the quantity of 1 plus R over N. So N times T. Okay, so we have filling in the specific values. Okay, so you have P is at 5,000. You have 1 plus, okay, you have R, okay, you have at 0.03. And N, okay, we're going to have at 2. And for the N times T degree, okay, so you have, so you're multiplying 2 and 6. And just looking at what we have now, okay, so you have $5,000. And 0.03 over 2, that's going to be 0.015, and adding to 1. So you have 5,000 times 1.015. And we have to the 12th power. Again, for 1.015 to the 12th. Okay, for many TI models, okay, we'll have that caret symbol. And for other models, you might have like a second function or button. You might have x to the y or y to the x. And then press the number 12 or enter the number 12. Okay, and then, okay, so for 1.015 to the 12th, okay, we have a number that'll be around 1.1956 and some decimal places after that. In other words, a figure just under 1.2. So at 3% compounded semi-annually, okay, the $5,000 is going to grow to right at $5,978.09. So that is going to be the future value. And again, just for the interest, Okay, that's going to be the future value minus the principal. So after 6 years, okay, you have around $978.09 to be added. All right. Okay, so we have this particular realm of compounding of interest. Okay, so you have going from simple interest to compound interest, and then we have in the remaining portion. Okay, so simple interest. Okay, you have compounding done ever so frequently. Compounding of interest. Okay, you have a change up in terms of the frequencies. Now we have in the third case. All right, now, and we say that okay, with n. Okay, we've gone from annual to semi-annual to quarterly to monthly to daily. But let's say that if I have non-stop compounding, as n approaches infinity, okay, what's going to happen here is that for the future value, okay, so we have p times, okay, the quantity of 1 plus r over n raised to the n times t as n approaches infinity. Okay, so this statement portion, okay, that is going to be affected. And that 1 plus r over n to the n times t as n approaches infinity. Okay, so that is going to become, we have p, and then we have the re-entry of the natural logarithm exponential base e, and this will be taken to the r times t power. And so this is going to be what is referred to as continuous compounding. Again, we have with this formula, again, we have a is equal to p times e raised to the r times t degree. And we'll say that, for example, okay, say we have if we're looking at determining a, and we'll say we have the same $5,000, is compounded continuously at 3% for 6 years. So just kind of taking from the page of the prior example with the semi-annual compounding, and then just translating the semi-annual to where the situation is where we have continuous compounding. So again, we have a is equal to p times e to the r times t. Okay, so p is going to be at $5,000. Okay, and we still have the same r, so r is going to be at 0.03. And t, again, we have for 6 years. And 0.03 times 6, okay, so that's going to be 0.18. Okay. Now again, you might see this as a second function, like e to the x. Now for e to the 0.18, okay, that number, you also have a little bit under 1.2. See, this would be about 1.1972. And some decimal places after this. And once we multiply by $5,000, okay, it's going to be a little bit closer to $6,000. And in the case of the future value, okay, the $5,000 will grow to 59.86 and about 9 cents. Okay, and again, just for the interest amount, so you had the 59.8609 for the future value after 6 years, after having put in $5,000. Again, so the interest built upon this. So after 6 years, again, you have around $986.09. Okay, and compared to semi-annual compounding, again, that growth was at 978.09. Okay, so you have about, yeah, right at an $8 difference. Okay, so the more frequently the compounding is done, even at the same quoted percentage rate, the higher the balance is going to be. But you're going to have kind of a saturation point that is reached, and kind of like how we got to the number e with the 1 plus 1 over x to the x. It's like the power can get larger and larger. Thus, you have the frequency increasing, but the rate of growth becomes virtually negligible.